Let us let us continue chapter 4. Last time we introduced how we can use do the derivative using several techniques: backward technique, forward technique, and central technique. Just to summarize here, these techniques all are derived from Taylor series expansions. So we started first by developing fx around xi, and then to obtain the forward scheme, we replaced x by xi plus 1, and then we replaced x by, for the second step, we replaced x by x minus 1 to get the backward scheme. Okay, so as you can see here, just by rearranging terms, we were able to find what is f prime xi in function of fxi plus 1, fxi, h, and the second derivative, second, third, etc. derivatives. And we have found that because this approximation consists of a truncation error, the term that we are neglecting in forward scheme is of order of h. Because as you can see, in general, here we are talking about cases with h smaller than 1. When h is much smaller than 1, then you are dividing here delta f by a small number. So we'll obtain here a large number. While taking into as assumption, f second and f third are not very large, so they are finite numbers. So when we multiply by h, then by h squared, then by h cubed, then we will get smaller and smaller terms. So when we do this truncation, the higher term will be this one, and it is proportional to h. This is why we say that in forward approximation, the truncation error is of order h. And we followed the same procedure to determine the expression of backward derivation. So in this case, also same method. First, we write the general expansion of fx about xi. After we replaced x in this expression by xi minus 1. So just we pay attention that delta x represent here, in general, delta x is equal to h, okay? So you can write it as xi minus xi minus 1. So since here you want xi minus 1 minus xi, you replace it by minus h. And then when you develop here, you have minus h squared. So for all even coefficients, you will end up with a positive result, while for all odd coefficients, so for third derivative, fifth derivative, etc., you will have a negative sign, and the sign will be alternating between minus and plus, which was not the case previously in the previous method, because it was just plus h. Okay, and now once we obtained also the approximation for the backward scheme, also we can deduce by doing truncation the dominant terms that we neglect are of order h. Now, from these two expressions, we can derive the central scheme by saying that the central scheme can just be obtained by adding the expression of derivative of the forward scheme plus the expression of derivative of the backward scheme and dividing by 2. Because once we do this, in this equation, we will have, when adding these two terms and dividing by 2, fxi will cancel out. And then we will have the expression desired, which is fxi plus 1 minus fxi minus 1 over 2h. And what is nice about the central method is that, as you can see here, after rearranging your terms for the forward and backward method and obtaining f prime, you will see that you will have opposite coefficients for the even derivatives. So f second, f fourth, f sixth, you will have minus and here plus, they will cancel out. So when you do the summation, you will only have the terms of odd derivatives. Okay, so it's minus h squared over 6f third, and then you will have the term for f fifth, etc. So when we do the addition, only the odd derivatives will remain, and therefore you can see that when you do truncation, your error, the term that is dominant in the truncation is the first term here. After 0, 0 will not affect the result. So it is of order h squared. This is why we say that in case of central difference, the error is of order h squared, while in case of backward and forward difference, the error is of order h. And since in general we work with h much smaller than 1 when we perform, because you know, for derivation to be accurate, starting from the definition of derivative, df over dx, it's the limit. So df over dx is the limit when delta x tends to 0 of delta f over delta x. So going from the definition of derivative to have accurate result, dx delta x should be small. So in general, this is why we say that because we will take h much smaller than 1, the central method will be more accurate than the two other methods. Okay? So let me check if you have any questions.
Doctor?
Yes?
Which we're putting for the centered h squared because it starts from the second degree and then h3, h4.
Because Karen, you have here that this term, okay, you are multiplying f third by h squared. So this term is dominant over all other terms. And since it's multiplied is proportional to h squared, then your error will be of order h squared. Okay? This is the reason. Because your term you are neglecting, the major term you are neglecting is proportional to h squared. So we say then that the error will be of the order of h squared. Okay? It will not be equal to h squared, but it's of the same order.
So we can remove O of h squared from the formula at the end.
Yes, here it's just, they are just saying, yes, of course, when you want to do the approximation, you will just take this term. But you will say that my error, what I am neglecting, will be of the order of h squared. Okay?
Yes, doctor.
Oh. So now we will take an example. We have the function of x equals to minus 0.4x4, minus 0.15x cubed, minus 0.5x squared, minus 0.25x plus 1.2. So here, when we derive this function with respect to x, we can get the exact value of the derivative. So here we are able to compare the exact value to the value that we can obtain using the forward, backward, and central difference approximation. In this problem, I asked to compute f prime for x equals 0.5 for different values of h equals to 0.5 and h equals to 0.25. So I will add a question. The question I will add is to compute the relative error, for example. So compute the relative error you will get. Okay? So in order to compute the relative error, the true relative error, I should know the exact value. So if I want to know the exact value, I should derive my function first to get the general expression of the derivative. Then I can find what is f prime at 0.5. So just the general rule to derive, for example, if you have x to the power n, the derivative will give you n times x to the power n minus 2. So if I derive fx, I will get minus 0.4 x cubed minus 3 times 0.15, which is 0.45 times x squared, minus 2 times 0.5x, so it's minus x, and minus 0.25. So in this way, I am able now to calculate the exact value by just replacing in f prime of x. I replace x by 0.5. I get then that the exact value is f prime at 0.5 is equal to 0.91 minus 0.9125. Now, what I will do, I will try to get an approximation of this value using numerical techniques. So using numerical techniques, when I want to compute the derivative, I have several schemes. We have introduced together the forward, backward, and central difference approximation. Let us start with the forward method. If I want to use the forward method with a step h delta x equal to 0.5, this means that I can write that delta x can be written as xi plus 1 minus xi, and at the same time it's also equal to x minus xi minus 1. When I use the forward scheme, I am interested in the value of xi plus 1. So I will set that delta x is equal to 0.5, which is h here. And I will say that from this relation, I deduce that xi plus 1 can be written as 0.5 plus x, and x of interest in my problem here is 0.5. So xi plus 1 will be equal to 0.5 plus 0.5 equals to 1. While xi minus 1 will be given by 0.5 minus x, okay, 0.5 minus x, and since x is equal to 0.5, so xi minus 1 will be equal to 0. Now I am ready to use the different schemes. To start with the forward scheme, from forward scheme I can write that f prime at 0.5 will be equal to fxi plus 1, which is 1. So it will be f at 1 minus f at x, which is 0.5, xi. So minus f at 0.5 over delta x, which is here. The step we used is 0.5. Now all I have to do is to get f1 and f0.5 just by replacing here x by 0.5. I get f of 0.5, and 1 I get f1. And now I can compute f prime, and I can put here the sign f, the subscript f, to say that this is the derivative that I can obtain using the forward scheme. Now, if I want to use the backward scheme, f prime backward, instead of using points x, so this is point xi plus 1, this is point xi. Instead of using xi plus 1 and xi, now I will use xi and xi minus 1. And xi minus 1 is 0. So the expression for f prime backward will be equal to f at 0.5 minus f at 0 over 0.5. And now I can get a new expression for f prime. It will be different, so it will not be the same value. And we can see which one is more accurate by calculating the error. Now, if I want to use the central difference approximation, okay, then I will say that for f prime central, I just want to use xi plus 1 and xi minus 1. So it will be f at 1 minus f at 0. And f at 0, I got it from the previous step by just replacing x by 0 here, over 2 times delta x, so over 2 times 0.5. Now I have all computations, 3 computations of f prime, and I want to see which one is more accurate. So I will go back now to the errors definition. We have defined together last time several types of errors, so just let us go back to them. The first type of error is the true error. So just you have to compute the difference between the true value, which you got from f prime at the point, so from the exact function, minus the approximate value. You have used 3 possible approximations, and you can see what will be the true error for these different approximations. Now, as I told you, the true error will not always, it can just give you what is the difference between the true value and the approximate value, but it will not tell you the percentage of error. So to know if it's an acceptable error or not. So if I just tell you the true error is 10 minus 4, it can be a very good error, it can be a very bad error. Because if the numbers you are working with are small, of the order of 10 minus 3, then your error 10 minus 4 is not acceptable. While if you have a true error of 10 minus 4, while the numbers you are working with are of order 10, then it's a good error, okay? This is why to decide if it's acceptable or not, the best way is to compute the relative error, which will give you a percentage of difference. So all you have to do then is to divide the true error by the true value. We will do this now in this example. Now, the other two types of error, I will go back to them, okay? So now just, we will apply these two, okay? Now for the approximate error, you can use it when you don't know the value, the exact value. So if I don't know the true value, then I can compute it by using the result of different iterations. So you know that in a numerical method, you might iterate. You do a first approximation. Then as you will see here, for example, in the example we are doing, we investigated first h0.5. We will find that errors are not acceptable. So we will move to a lower h, let's say 0.25. And we will see then that we can compare, we can find the approximate relative error by taking that the approximate error will be the difference between v nu, which we got, so f prime nu here, which is the one we get at 0.25, minus f prime we got at 0.5 over f prime nu at 0.25. So in this way, this error is possible to calculate even if we don't know the true value. Okay. Now, for the absolute error, the final type of error, we will not be able to calculate it in this chapter because the absolute error here, we mean by it, it's not just, it doesn't mean the absolute value. In general, any error you find, you just give the absolute value because we don't care if it's positive or negative. But there is another meaning when they just tell you find the absolute error. This means find the maximum possible errors that you can have in a method. Okay, and this type of errors is not involved here. It will be involved in next chapter when you have an interval for the error. And for example, if you want to find fx equals to 0, and you want to find for which value of x I have fx equals 0, you can tell me, I can give you an interval. So in this interval, the solution will be, but I don't know exactly where it is in the interval. This means that the maximum possible error will be the boundary, the difference between the boundaries of the interval. Yani for example, if I tell you the error, the exact solution for fx equals 0 is between 1 and 2, but I don't know where it is. So then you will tell me, in this case, the maximum possible error is 1, for example. Okay? Here, it's not the case because we are not putting any interval for the value. We are finding a certain value, and we are comparing it with the previous one or with the true value. So remember just this definition. We will see it in detail in next chapter. Now, for true error, true relative error, and approximate relative error, in general, you give the absolute value without putting the sign. You can put the sign, but it will not give you any addition. So we don't care if the true value is smaller or larger than the approximate value. We care for the difference, the absolute value of difference between. In this problem, I will try to introduce for you all of this, the first three types of errors, to see how we can calculate them. So here, in this slide, you can see the three techniques and the resulting values. So if I start by the forward difference, it will give me a value of minus 1.45. And I want to compare with minus 0.9. I think it was 125. Let us make sure. Yes, it's minus 0.9125. So I want to compare now. I want to calculate. I can calculate the true error. I can calculate the percent error now, the relative error, the true relative error. So first, if I just want to calculate the true error here, E true, capital letter, T subscript, it's equal to the exact value minus the approximate value. So minus 0.9125 plus 1.45. Okay, so in this case, I will get a negative result. I will get, sorry, a positive result for the true error. Okay, but if I calculate the relative error, I will get a negative result because the true error, relative error, is defined as the true error over the exact solution. Here it's v prime, f prime. So here f prime exact. So if I want to find epsilon true, Okay, I will divide this result, which is a positive number, by the exact value, which is negative. So I will get a negative result. By here, they just represented the positive result because I told you that in general, we take the absolute value because we don't care for this. Okay, so in absolute value, I will get a relative error of 59% for the forward difference. For the backward difference, I will repeat the same procedure. If I want to find the true error will be just the true value, which is minus 0.9125. But instead of doing plus 1.45, I will do plus 0.55. Okay. So here, for example, the true error is negative, while in the forward difference it was positive. So now if I calculate here epsilon true, I will get a positive or negative result now. I'll get a positive result because E true is negative. Because when you do minus 0.9125 plus 0.55, you will get a negative result. Then you will divide by the true value, which is minus 0.9125. So you will get a positive result, which is plus 40%. Okay. But in order to compare, I just compare the absolute values. So 40% is smaller than 59%. So it's fine. This method is better. In this example, the backward difference is better than forward difference. It's not always the case, okay? But here, in this example, it was the case, okay? Now, if I continue, as I told you, in general, both errors of order h, but this is in order of magnitude. It's not the exact. It's not exact. Okay, 100%. So, but you can see that they are, relatively, they are little bit. The errors are not very far from each other. While when you do the central difference method, you will see a large difference because the central difference method is of the error in it is of order of h squared. And since you are taking h smaller than 1, then you expect to enhance your prediction when you use the central difference method. So when you use the central difference method, you get a relative error much smaller than the case of forward and backward methods.
Doctor,
yes?
Then why do we do forward and backward if we know that we're going to obtain a higher error? Why don't we go directly to the center?
Because you will see when you deal with engineering problems. For example, I will give you a simple example. In thermal mechanics, okay, you have, for example, heat transfer can be done by conduction, by convection, by radiation. Okay, if you write the terms of convection and conduction, you will see that in conduction case, the forward scheme, the centered scheme will be the best representation, because when I take, let's say, del T over del X, I will take 1 point before, 1 point after. But when I deal with convection, as the flow is moving, okay, you will see that in this case, the central difference method will not give me maybe as accurate method as the upwind scheme, which will take just the value at a point and the point just after it. So from experience, when you deal with a certain type of science, you will see that for each phenomena, one of the scheme might be better to use than the other. Okay, so to go in deep details for this, you should understand well the science of each. For each science, for each equation or each type of, let's say here we are talking about heat transfer. Let's say in convection, for you, it's good to use an upwind scheme which will take a forward difference instead of central difference, let's say. Okay.
So for this function, the central is better, we can say.
Yeah. So here, if you want, here we are computing derivatives. Okay. So we are saying we are seeing here that it's good to take central difference scheme. Sometimes maybe also for if you want in other, this forward scheme is not only used for derivatives. So the idea of forward, backward, and central difference scheme is not only used for derivatives. This is what you should understand. So after, when you are working after, you should know what is an upward scheme, a forward scheme, what is a backward scheme, what is a central difference scheme, and depending on the application, you can have that a scheme can work in a way better than the other. Okay.
Yes, doctor.
So here, when you are just interested into a derivative, okay, it seems that the central difference scheme is working much better. While if you have maybe just a difference, if you don't have a derivative, Karen, if you have just to compute delta f, you can compute delta f in several ways. You can compute delta f using forward scheme, backward scheme, or central difference scheme. You can see that depending on a certain example, some examples will work better with forward scheme than with central scheme. Okay?
Yes. Okay. Yes, doctor.
Now, if I ask you here to compute the approximate relative error, you cannot calculate an approximate relative error if you just have one iteration. You should have performed more than one iteration. So here, for example, you will put a criteria. Let's say you will say I will stop I will stop to do iterations once I reach epsilon smaller than epsilon. Let's say the relative value smaller than 5%. Okay, here let us put not epsilon true. If you are working, let's say, I will put the criteria for epsilon true, but I will tell you how you can calculate the approximate error. So if this is my criteria, I cannot stop at this iteration because for the three cases, I have epsilon larger than 5%. Now, this is why I will say what is the strategy in general to reduce the error is to reduce h. So I will go from 0.5 to 0.25, and I will repeat the same procedure to be able to calculate the error. And as you can see here, because you know that the order, your error is of order h in forward and backward scheme, you can expect that if I divide h by 2, I can nearly divide then also the error by 2. And this is what will happen. Because look, I nearly moved from 60 to 30. It's not 100% divided by 2, because you know, I'm not only neglecting the term of order h, but I have several terms that are neglected. But the dominant one is of order h. So when I divide h by 2, I expect to nearly, approximately, the error will be divided by 2. And this is the case, because it was nearly 60%. Now it's nearly 30, close to 30%. While for the backward difference scheme, it was 40 and now it's nearly 20. So approximately the error is over 2, as I expected. While for the central difference scheme, because the order in the central difference scheme is h square, then when I divide h by 2, I can expect that my error can go over 4. So my error then will be approximately over divided by 4. And because it was nearly 10%, now it's nearly 2.5%. So the only scheme that satisfied the criterion is the central difference scheme. So if I choose the central difference scheme to compute the derivative, then I will stop at the second iteration. While if I use the forward or the backward scheme, I should continue. I should proceed until reaching epsilon true smaller than 5%. Now, because you perform 2 iterations, I can ask you to calculate what is the approximate relative error. So if you want to calculate the approximate relative error, the technique is to take f prime nu at the new iteration minus f prime at the old iteration over f prime nu. So for example here, if I want to assess the approximate error for the forward difference scheme, I have the new value is minus 1.16. I have the old value is minus 1.45. So it's minus plus 1.45 over f prime nu, which is minus 1.16. Okay, so in this way, I can calculate what is the approximate relative error. And in case I don't know the exact solution, I will have a criterion for the approximate error to know at what time to stop. Okay? Any question on this? Let me check your chat. Look, you can start with a small value. Okay, it's right. You can tell me I can start from beginning by 0.25. Yes, it's fine. Okay, and you can start maybe by 0.1. So you are free to take your initial step. Okay, Yes, it's true. It's good to start with a small h because we expect that with smaller h we can get a better value. Here, just the purpose is to show you how we proceed. Okay, so let's say maybe if you require a very accurate result, if let's say you want to stop when epsilon is smaller than 10 minus 6, maybe even if you start by 0.25 or smaller, you still not your criteria is still not satisfied. So what should you do? You should proceed with smaller h. So you should start somewhere. Yes, it's good to start with with a small number, enough small number, because this is expected to give you a good result. But you will see together that if you decrease a lot h, it will give you bad results, and you will see this in this session. Okay. Yeah. So let us continue. Now, concerning yesterday, we have talked a little bit about how to go from base to base. Okay. Now we will go back to this idea, and we will develop general techniques that will allow us to go from decimal to binary system easily. Okay. So, for example, here, if I have this number 602.9, so this is expressed in base 10. And I can write it in the following way. I can decompose it as 600, which is 6 times 10 square, plus 0 times 10. Okay, because here I don't have any number to the order of 10 power 1, plus 2, which is 2 times 10 to the power 0, plus 0.9, which is 9 times 10 minus 1. So whenever we say it's base 10, it's called base 10 because we can just have 10 possible digits, which are digits from 0 to 9. Okay. Now, in case of base 2, we only have numbers 0 and 1. Okay. And you can define any base you want. You can define base 5. For base 5, numbers would go from 0 to 4. But the commonly used type of base are base 10 and base 2. Okay. But all other, you can have a different type of base 4, base 5. So it's the same concept. Base 10, all digits will go from 0 to 9. Base 9, digits will go from 0 to 8, and etc. Okay. Now, for example, if I want to write 5.5 in base 2, how to do this? I can divide 5.5. I can write it. So for simple numbers, I can do it without developing a very complex technique. So what I can do, I can say if I can write 5.5 in a way as combination of numbers. So if I have 2 square, 2 1 and 2 0, I want to try to combine them in a certain way. 2 square is 4, and 2 to the power 0 is 1, and 2 to the power 1 is 2. So you can easily see that 5 is simply 4 plus 1, okay, which is 1 times 2 square, and you don't have any term along 2 power 1, so it's 0 times 2 power 1, plus 1 times 2 power 0, plus I still have 0.5. 0.5 is just 1 over 2, so it's 2 minus 1. So it's plus 1 times 2 minus 1, and I get it. Okay? I can have little bit more complex example. Let's say if I take 9, for example, 0.5. So 9, I can say that 9, I can divide it into a multiple of 4, which is 8. Okay, let's say 8 plus 1, but it cannot work here because look, I will need to put 2 times 4, and 2 is not a number that I can present in case of base 2 because I just need 1. Okay, I just need 1 or 0. So I should think in another way. I should decompose 9 and not as 8 plus 1. I should try to decompose it in a different way. Okay, so because I might do this by trial and error, but in order to have a technique that can directly give me the result without doing trial and error, we will develop together now how to convert from decimal to binary. Okay. So this is the technique. It's a very simple technique. I take the number, let's say 7 in base in base 10, in decimal base. I want to convert it to base 2. So what I do, I start by dividing by 2. It gives me 3, remainder is 1. Now I take the number I got here, 3. I divide 3 by 2. I get 1 with remainder 1. Finally, I have 1 over 2. It gives me 0 and remainder 1. Once I reach 0 here, I will stop, and then I can read the value of my number in binary base by reading from bottom to top. Please pay attention, from bottom to top, not from top to bottom. Here it's the same because it's a symmetrical number, but it's wrong to read from top to bottom. You read from bottom to top. Let us take another example, 13. So same method, I divide first by 2, I get 6, remainder 1. Now I take